you so much. Okay, see you soon later.
Oh, you will exit from this meeting or waiting
Accept? What?
or just in this meeting?
Sorry, what do you mean?
No, no. You stay in this room, right? Until 1 p.m.
Yeah.
Yeah. Okay.
Okay, I will start at sorry. We will start 1 p.m. in
Yeah,
Indonesia.
yeah. Maybe there is a host that will open this meeting, and after that, so maybe I will explain, yeah, about the timeline of this meeting. So at the first, maybe it is opening section by host. And after that is opening speech from our representative of my department. And then after that, host will ask you to deliver your material. And after that, it is a discussion section. And after discussion section, it is closing. Okay.
Okay. Thank you so
So
much.
yeah, that is the timeline of this meeting. Okay. Are you in campus or in?
Yeah, sure.
Oh,
I'm
yeah, yeah.
campus.
Okay.
So now I'm using just one room alone.
Yeah,
Basically,
yeah,
we are in the same room, but for now,
yeah. Actually, I also invite Professor Fuyuki and also Professor Shimamura and Dr.
yes.
Akihide. But only Professor Fuyuki and Dr. Akihide
Akihide.
reply my invitation.
Yeah,
So
they should be
maybe
very busy.
it's like reunion for us.
Thank you. Okay,
I
I'll
want
do my
to
best.
invite Kai, but I cannot get his email address, and I try to text via line, but he don't reply me. I don't know why. Is he still in Kumamoto or he
Maybe
is graduate?
he's studying abroad now because he's a doctor student. First grade.
Yeah, yeah, yeah.
Yeah, he should be in the US.
In the US. Oh, I
Maybe,
see, I
maybe.
see, I see. And how about Hinata? Is she graduate?
Hinata got a job in Japan. It's all I know about her.
Oh, but she is graduate, right, from Kumamoto.
Yes. Is it okay to talk here?
Okay, okay. It will start at 1 p.m.
Okay, okay.
Yeah. Hello, Kaura Sensei. Can you hear my voice?
Yes.
Can I
hear me?
Yeah, yeah, it's clear from here.
Oh,
Finally, we can meet again.
ya. Selamat siang, Erik.
Ya, selamat siang.
Long time no see.
So here
Yeah, long time
also
no see.
attend Prof. Eko. He is representative from our department in physics department Universitas Diponegoro.
Nice to meet you.
And Prof. Eko also graduate from Japan, right? For doctoral program.
Konnichiwa, Kaura Sensei and Tokushima Sensei. O genki desu ka?
ああ、あれ日本語がお分かりになる。
Yes, yes, yes. Like Eric Sensei said that I am graduate from Kyoto University
Oh,
18
I
years
see.
ago. It's a long time.
ああ、はじめまして。スラオスやん。
Selamat siang.
Yes. Also, I came from Yario Kogaku, Yario Kagaku, Sensei. Material Science.
I'm sorry, Kora Sensei.
Yes.
I also invite Shimamura Sensei, but he didn't reply me.
ああ、
Yeah.
he looks like
Busy or
rather busy. Yeah.
yeah.
I'm sorry.
No problem. No problem. How many students now in Shimizu
laboratory?
Sensei? Yeah.
えーっと、one doctor course student and she, she, she got some, she, five master course students and
Five master. Okay.
five beyond students.
Yeah. For doctoral, one student. Yeah.
Yes.
Oh, yeah.
But in fact, meaning it is combined laboratory. That is the Shimojo laboratory and Shimamura laboratory.
Oh, I see. Yeah. Oh ya, yes. Bukan. Oke, baik. Mungkin dimulai eh, 2 menit lagi ya, Pak Dani ya, untuk acaranya.
Oke.
Okay, ladies and gentlemen, before we start this lecture, we encourage everyone to please turn on your camera and kindly use the official virtual background that has been provided by the committee in the chat box. Bapak, Ibu, saudara-saudari sekalian, sebelum kita mulai kuliah kita pada siang hari ini, kami harap bisa menghidupkan kamera serta bisa menggunakan official virtual background yang sudah diberikan oleh panitia pada chat box di ruang Zoom kali ini. Terima kasih. Thank you.
Oke, bisa dimulai, Pak Dani.
Oke, thank you. Ya. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Good afternoon. Good afternoon, ladies and gentlemen. The Honorable Assistant Professor Sugu Fukushima, PhD, from Institute for Material Research, Tohoku University, Japan. The Honorable, the Head of the Department of Physics, Universitas Diponegoro, Professor Dr. Heri Sutanto, or in this occasion will be represented by Professor Dr. Engineering Eko Hidayanto. Respected lecturers, colleagues, and dear students, it is my pleasure to welcome you all to today's general lecture. First and foremost, let us express our gratitude to God Almighty, for it is by His grace that we are able to gather virtually for today's general lecture. with a very timely and exciting topic, machine learning potentials and its application for material science. Allow me to introduce myself. My name is Dani Nur Indra Syamputra. You can call me Dani. I am a lecturer from the Department of Physics, Universitas Diponegoro, and I will be serving you as your host and moderator for today's general lecture. Ladies and gentlemen, before we begin, let me share with you the agenda for today's session. The first one is the opening session, which we have just carried out together. The second will be the welcoming remarks from the head of Department of Physics, Universitas Diponegoro. After that, we will have the presentation of the lecture material by our distinguished speaker. And then we will have the discussions and Q&A session with the speaker. And after that, we will have the certificate awarding to our speaker as a token of appreciation. And the last one, we will have the closing session. And that will be the flow of our program today. So to formally begin our event, let us first listen to the welcoming remarks from our head of the physics department, Universitas Diponegoro. That will be presented by Professor Dr. Eko Hidayanto. To the Honorable Professor Eko Hidayanto, we kindly invite you to deliver your remarks.
Thank you, Mr. Dani. Baik, Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam warahmatullahi wabarakatuh.
Ladies and gentlemen, good afternoon. Konnichiwa. Welcome to today's general lecture. First of all, let's us to express our gratitude to Allah Subhanahu wa Ta'ala by His grace that we can get here today. On this occasion, we have special lecture. Eric Sensei friend, I think. His name Sogo Fukushima Sensei, right, Sensei?
Yes.
Yes. He from Tohoku Daigaku no Kinzoku Zeryo Kenkyujo. Is also right, Sensei?
Yes, right.
Okay. Undip Putsurigaku Yokoso. Selamat datang. Welcome to Department of Physics, the Diponegoro University. As you know that watashi mo Kyoto Daikeku no Yaryo Kagaku o Manande Imasta. So about 80 years ago, 2005 till 2008, I was learned about material also. And today, Fukushima Sensei will give the topic about machine learning potential and its application for material science. I think it's very interesting topic like this. Okay, ladies and gentlemen, the rapid development of digital technologies, particularly machine learning, has opened up remarkable opportunities across many disciplines, including the material, of course. With this approach, we are able to accelerate the discovery of new material, optimize existing properties, and gain deeper insight into complex phenomena that may be difficult to analyze using conventional method. So we will use this machine learning like this. Through this lecture, we hope to broaden our understanding how machine learning can play the transformative role in this research, innovation, and practical application in the field of material science. I hope also that this event will inspire us to collaborate further and foster innovation for the advance of knowledge and its benefit to society. Finally, in the name of department, I would like to thank our distinguished speaker, all participants, and also everyone who has contributed to this lecture. In the name of Allah, by saying Bismillahirrahmanirrahim, with the permission of all of you, all the participants, I open this public lecture. Okay, thank you for Mr. Sensei Fukushima. Welcome to our department. Thank you very much. Domo arigatou gozaimashita. Thank you, terima kasih. Okay, I back to Mr. Eric, Mr. Dani, please, Mr.
Okay. Yeah, thank you, Prof. Eko, for your opening remarks. So, ladies and gentlemen, before we go to today's main session, we would like to kindly invite all participants to join us for a group photo session. So, we encourage everyone to please turn on your camera for a moment, and if available, kindly use the official background that has been provided by the committee. Let us take a few seconds to prepare. Okay, please open your camera. Okay. Okay. Yeah. All right. I see many of you are ready. Let's capture this wonderful moment together. So I will count down. 3, 2, 1. Smile. Again. Let's take another one. 3, 2, 1. Smile. Okay. Yeah. Okay, thank you very much for your participation. This photo will surely be a beautiful memory for today's event. Okay, ladies and gentlemen, we now dive into the main session of today's lecture. Today we gather to dive into one of the most powerful and transformative tools in modern science. Uh, as we know, machine learning, with the theme of machine learning potential and its application for material sciences. We will explore how machine learning is not only revolutioning data-driven fields, but also it could be a new opening for new frontiers in understanding, designing, and discovering advanced materials. To bring this closer to our context, let me share some simple cases. In traditional material science research, students and researchers often perform experiments to measure a single property of materials, such as hardness, conductivity, or thermal resistance. And then we analyze the results manually. While this is a valuable exercise, it is often takes a lot of time, resource, and sometimes it provides only limited insights. So this raises an important question. How can we go beyond these conventional methods and use machine learning to predict material properties, accelerate discovery, and even design new materials with desired functionalities before they are physically fabricated? And this is exactly the kind of challenge, that opportunity that today's lecture will help us to explore. And to help us explore this topic on machine learning potentials, we are truly honored to have with us an inspiring researchers and academician. Our distinguished speaker is Dr. Shogo Fukushima. Hello, Dr. Shogo Fukushima.
Yes, how?
Yeah, nice to meet you.
Nice to meet you.
Thank you for your participation in this event. Uh, Let me introduce Dr. Shogo Fukushima first. He currently serving as an assistant professor at the Institute for Material Research, Tohoku University, Japan. Dr. Fukushima has a strong academic background. He completed his master degrees in 2018 until 2020 and PhD in 2020 to 2023 at the Graduate School of Science and Technology, Kumamoto University. During his doctoral journey, he was also awarded the GSPS Research Fellowship for Young Scientists, di situ, in 2021 and up to 2023. And he gained valuable international experience as a visiting research assistant at the University of Southern California. his research focus on advanced computational approaches, particularly in non-adiabatic and non-equilibrium first principles molecular dynamics, as well as machine learning molecular dynamics. He has published impactful works such as studies on the photo-induced phase transition of diamond, the dielectric properties of alumina films, and the application of neural network potential for thermodynamic integration. This contribution places him at the intersection of material science, physics, and machine learning, the fields that are rapidly shaping the future of our technology and innovation. So that is the profile of our distinguished speakers for today. So before we begin, allow me to remind you that after the lecture session, we will have a Q&A session. You may write your question in the chat box at any time during the presentation, and I will select several of them to be addressed, or you will have the chance to raise your hand and ask directly after the talk. And also, please fill the attendance list given by the committee in the chat box. So now, without further ado, let us warmly welcome Dr. Shogo Fukushima to deliver his lecture. Dr. Fukushima, please, the time is yours.
Okay, please let me prepare my screen. Please let me share my screen. Okay, is it okay? Can you hear my voice and see my screen?
Yes.
Okay, thank you so much. Okay, thank you for invitation. At first, I appreciate for inviting this seminar and giving me such a valuable opportunity. My name is Shogo Fukushima. I'm assistant professor in Institute for Materials Research, Tohoku University. I'm sorry in advance. Please note that my speak may be poor due to lack of experience in lecturing English. Today, I would like to talk about machine learning potential and its application for materials science. At first, please let me introduce myself a little bit. I am Shogo Fukushima, an assistant professor at Kubo Laboratory in Institute for Materials Research, Tohoku University. When I was a master and doctor student, I studied about computer physics at Kumamoto University. When I was doctor student, I was conducted a research with JSPS Research Fellowship for Young Scientists DSC2 and studying abroad to University of Southern California in the US. At this time, the restriction due to COVID-19 was very hard to communicate and discuss in person. And yeah, by the way, just before I graduated from the university, Dr. Eric came to Shimojo Laboratory in Kumamoto University, and we conducted research together. After that, I got a PhD, and from 2023, from 2023 to now, I have conducted the research as an assistant professor in Tohoku University. The research is mainly two topics. One is non-adiabatic, non-equilibrium first principles molecular dynamics. For example, we recently published a paper about photo-induced phase transition of diamond using a non-adiabatic quantum molecular dynamics study. Before that, I investigated the thickness dependence of dielectric constant of alumina film based on first principles calculations. The other one is machine learning molecular dynamics. We published a paper about the thermodynamic integration by neural network potential based on first principles dynamics calculations. I would like to introduce my research thesis a little bit. I studied lots of molecular dynamics simulation method and its development under Professor Fuyuki Shimojo in Kumamoto University. And I visited I visited the core laboratory for advanced computing and simulation in University of Southern California. Thanks to this professor's kind lecture, I could conduct lots of research. For example, I investigated the dielectric properties of alumina by applying electric field based on first principles calculations. Our laboratory investigated the thermal conductivity of superionic conductor AZ2SE before and after phase transition. And I studied about the phase transition mechanism based on first principles molecular dynamics. Recently, I published a paper about the photo-induced graphitization of diamond with Professor Aichiro Nakano. After graduated from Kumamoto University, I moved to here, Kubo Laboratory in Institute for Materials Research, Tohoku University. And I am working on 2 theses. This laboratory has mainly 3 research theses, but I am working on 2 theses. One is a stress corrosion cracking of high entropy alloy. High entropy alloy is an alloy composed of 5 or more metal elements in equiatomic proportions. Its feature is high mechanical strength, but easy to stress corrosion cracking, the growth of cracking formation in a corrosive environment. To investigate this mechanism, we create machine learning potential which can handle 5 metal elements and corrosive molecules like water, and perform tensor simulation like this animation. Okay, the other is tribe chemical reaction of friction modifiers. Molybdenum ditching carbamate, MODTC, is one of the friction modifier and makes the friction force decrease. To investigate the decomposition mechanism of MODTC, we construct the machine learning potential which can handle 6 elements in MODTC and iron.
Nah, kalian sama kan?
Sorry, someone is speaking.
Tadi mikrofon Pak.
Sorry.
Is it okay to continue? Okay. To investigate the decomposition mechanism of MODTC, we constructed a machine learning potential which can handle 6 elements in MODTC and iron. In this simulation, cluster consisting of molybdenum, sulfur, and oxygen atoms are created, and it can be considered as a precursor of MOS2 film and MO3 crystal, which are caused of friction, decrease, and wear, respectively. We are challenging to elucidate the complicated reaction mechanism of multi-element system. Okay, from now, I talk about machine learning potential. This is outline. At first, I will introduce abstract types, history, features, and so on of machine learning potential. Machine learning potential is a high accuracy interatomic potential predicted and produced by machine learning, developed by Baylor and Parinello in 2007 at first. From the atomic structure, configuration in the finite cutoff region, feature vector is created as an input of neural network. The feature vector includes distance of center atom distance and angle of atoms. The neural network outputs the atomic energy of center atom I. By taking a summation, the total potential energy can be obtained. And by calculating the gradient of potential energy at position I, atomic force on atom I is obtained. And stress tensor can be obtained from the derivative of infinitesimal strain. These predicted values can be added, such as charge and magnetic moment and so on. It depends on the machine learning potential models. The machine learning potential is trained by optimizing the parameters in the neural network so that the predicted values match the correct values obtained from DFT. Machine learning potential is represented MLP. These are the same meaning. But some authors use machine learning interatomic potential, so MLIP. These are the same meaning. If the MLP is neural network type, it is also called neural network potential or neural network interatomic potential. And some also use high-dimensional neural network potential. But they are the same meaning, basically. In this seminar, I will use MLP. This is the history of the development of MLP shown in the following review papers. As I introduced, the first MLP developed by Vela and Parinello in 2007. After this, different type Gaussian and polynomial type MLPs are presented and the number of LMP models increased rapidly. Recently, the graph-based equivariant type MLP is attracting attention. I will explain about these graph and equivariants later. Here, I explain the merit of MLP by comparing other methods. Interatomic potential is needed for time evolution of atomic structure. In the case of classical molecular dynamics, using empirical potential like Lennard-Jones potential, potential energy and atomic force are computable analytically. So it is very fast but low accuracy. Reactive force field and embedded atom method may be able to include this case. In the case of first principles molecular dynamics, such as density functional theory, electronic state calculation based on Kohn-Sham equation for all electrons are needed. So it is high accuracy but very slow. On the other hand, MLP can reproduce the energy and forces obtained from DFT with formula computable analytically. The calculation cost can be greatly decreased while keeping the DFT accuracy. There are lots of difficulty and devices to construct high accuracy MLP, but the merit of MLP should be very large. In the training, the parameters in the neural network are optimized so that the predicted values matches the correct values obtained from DFT, as I explained. This principle is the minimization of loss function. Loss function consists of errors of energy, force, and stress terms. Some additional terms, such as charge, can be added depending on the model. The formula whose terms are normalized in the per atom and per frame is presented. Minimizing loss function means a minimization of total errors of energy, force, and stress. Each term has a weight parameters PE, PF, and PP. They can be used to adjust the training like weights. For example, you want to train with larger weights on force. It is okay to use 110, 1, or 100, 1, something like that. The balance of the weights parameters is also important. By calculating the gradient of loss function with respect to parameters W in the neural network and update the parameters based on this gradient, the training can be run. Next is the activation function used in the neural network. Its role is increasing freedom of expression by nonlinear functions. There are lots of types of activation functions like hyperbolic tangent and sigmoid and so on. In the selection of activation function, we need to consider vanishing gradient problem of loss function. The derivative of, this is a general problem in machine learning. In the calculation of gradient of loss function, the derivative of activation function is the derivative of activation function appears. If this derivative is 0, the training stops. Maybe you can understand easily by seeing the previous piece figure. So if the gradient is 0, the training is stopped. And maybe you can, if the gradient becomes 0, the parameter does not move anymore. In the case of MLP, it affects on the force calculation because the derivative appears again here. The selection of activation function depends on the objective, such as image recognition or generative AI, but Swiss or sigmoid-weighted linear unit still function is often used in the MLP. Its feature is non-linear differentiable and the differential tends not to become 0. Next topic is overfitting. This is one of the general problem in machine learning. In the training, the data should be separated in train data and the test data. The former is used to train and the latter used to check whether the loss decreases for not only trained data, but also non-trained data. Errors on trained data naturally decreases, but if errors starts increasing on test data, overfitting occurring. The schema is left figure. While the loss on trained data is decreasing, the loss on test data increasing. This means that the fitting is okay, left curve, but between the two trained data points is not good, like from here to here. Therefore, if we answer the question, when is overfitting likely to occur, it should be when the number of parameters is too large relative to the amount of data. While increasing the number of parameters can improve accuracy, basically, it simultaneously makes the model more prone to overfitting. Okay, this is the final topic in the fundamental of MLP. It is symmetry. In the case of MLP, some symmetry must be satisfied. For example, energy of molecules does not change after rotate. So MLP must satisfy the rotation symmetry. Similarly, MLP satisfied inversion, translation, and permutation symmetries. From the initial letters of these symmetries, some MLP developers call TRIP. To satisfy TRIP symmetry, each MLP model has device that the basic is use only bond angle, relative atomic vector, and elements. Okay, from now, I would like to introduce some MLP models. First, I explain about the Bela polynomial time MLP, which is first MLP models. From the atomic structure obtained by DFT calculation or FEMD simulation, the atomic coordinates are extracted. The coordinates are converted to symmetry function as an input of neural network. The set of symmetry functions is a feature vector of this MLP model. Finally, atomic energy is outputted and the total potential energy is obtained by taking summation. The detail of structure of neural network is like this. Here consists of input, hidden, and output layers. In the case of left structure, the obtained atomic energy is this formula. Z is the symmetry function, W and B is weight and bias parameters in neural network, and F is the activation function. MLP can reproduce the DFT energy by MLP can reproduce the DFT energy and force by optimizing W and B. The formula of symmetry function is as follows. There are several types of symmetry functions, but I would like to introduce two used mainly. One is a radial symmetry function. This function is based on Gaussian. Rij is a distance between atom I and J. Fc is a cutoff function. various symmetry function set created from the parameter set eta and rs. This table is a parameter set I have used, and specific functions are shown in right figures. To increase freedom of expression, lots of parameters eta and rs are needed. The other is angular symmetry function. Theta ijk is the angle between atom ij and k. Similarly, various symmetry functions are created parameter set eta, lambda, and zeta. Like this. This MLP model represents information around atoms using symmetry function as a basic. Second MLP model is atomic cluster extension, ASE. This is a polynomial type MLP using complete descriptor of the local atomic environment, which can represent previous descriptors used in the other MLPs, such as Bera-Parinello symmetry function. The single particle basis is created by radial function and spherical harmonics to divide it in the information into radial and angular, like a symmetry function. Atomic neighbor density basis and many-body product basis are constructed by taking summation around all pairs within finite cutoff. To satisfy the trick symmetry, symmetrization is done using Krebs-Gordon coefficient. Finally, total potential is fitted by linear combination of basis B. The feature of ACE is invariant to trip, that means satisfies the symmetry. And previous descriptors like Bera-Parinello symmetry function can be described in basis B. A third MLP model is deep potential, DeepMD kit. Deep potential was developed by Professor Zhang in 2020, and it is a winner of Gordon Bell Prize. Maybe this model is most famous model. Here, the explanation of architecture is skipped, and the feature is invariant to trip symmetry. And the architecture is simple compared to other MLP models. This means the number of hyperparameter is small. And this model has two neural networks. Embedded networks optimizes descriptors, that is, feature vectors, and fitting network optimizes output energy. They push the limit of molecular dynamics to 100 million atoms with ab initio accuracy. From here, I'd like to introduce graph-based MLP model. Before that, please let me explain about graph. A graph is an abstract data type consisting of nodes and edges used in a graph theory. A node is a circle, and the edge is line connecting nodes. Molecular structure can be reviewed as a graph composed of nodes, atoms, and edges, bonds. The first graph-based MLP model is NeQuip, developed by Materials Intelligence Research, MIR group in Harvard University. There are two keywords in the feature of this model. The first one is equivariant to trip symmetry. I will explain about this in detail later, but this means increase of data efficient. In other words, this model has high accuracy with small training data. The second is a graph convolution neural network. All feature vector of adjacent nodes are incorporated. This means multi-body interaction can be described. These features make these models' accuracy higher than other ML models. The last feature is a long-range interaction can be incorporated due to the multi-time message passing. Message passing means like a graph convolution. For example, all nodes can get a feature vector of not only first, but also second neighbor nodes by second-time convolution. If the number of times of convolution is 3, the all nodes can have features of until third neighbor nodes. This makes the accuracy higher and higher, but parallelization becomes more difficult. In other words, the computational cost becomes large. To decrease the computational cost, MIR group developed Allegro model. This MLP model is used in our laboratory. This is an improved MLP model of NEQUIP, which is one of the finalists of Gordon Bell Prize in 2023. The features are almost same as NEQUIP, but feature vectors calculated from strictly local. Due to this improvement, it has efficient parallel scalability. That is, the computational cost can be decreased. Allegro model has been demonstrated using more than 100 million atoms. By the way, Allegro means fast in the musical terms. Here, please let me explain about the invariant and equivariant. This is a concept of mathematics to present symmetry. Let us consider to feature vectorize to and rotate input x. One is a feature vectorization and rotation. The other is feature vectorization after rotation. If phi x is equal to phi zx, it is specified in invariant to rotation. On the other hand, if z prime phi x is equal to phi zx, it is equivariant to rotation. Therefore, invariance is the special case of equivariance when z prime is the identity transformation. In the case of invariant, phi decreases information of zx. That is, it is impossible to judge whether the molecule is rotated or not. Let me explain using the molecules as an example. This is methanol molecules. Let us consider to calculate atomic force via feature vectorization and whether satisfies the rotation symmetry. The final atomic force should be matched before and after rotation. That is, obtained atomic force must be rotate same as molecules. This symmetry is natural requirement from MD simulation. This symmetry is natural requirement from this MD simulation. In summary, this is the image of invariant and equivariant. Please note that this explanation is not strict, like an extreme case. Left is invariant, right is equivariant case. In invariant case, the atomic force does not change after rotation, but this is not good if you can understand easily. In equivariant case, the atomic forces are rotated in accordance with molecular rotation. This is the importance of equivariance. Okay, next, I would like to introduce the application of MLP model focusing on Allegro model. Yeah, this is the application examples of Allegro. For example, Professor Maxton investigated the transferability of water. They tried to reproduce not only liquid but also ice, liquid, and vapor phase by training only liquid water data. And for example, transferability for ionic liquid are also investigated. Nuclear quantum effects for ammonia and structures of alkali halide. Professor Smeria investigated about a comprehensive search for active sites for CO2 on kappa protein nanoparticle on TiO2, like graphical abstract. So Professor Hartley demonstrated the revisiting aspirin polymorphic stability and free energy calculation by sharing simulation. Professor Shimamura tried to calculate thermal conductivity with high accuracy of superionic conductor H2SE by using Allegro potential. For now, let me introduce the application example of our laboratory. First one title is a neural network molecular dynamics simulation of friction-induced chemical reaction of SiO4 in water and ethylene glycol environments. This research is about a water lubrication, which is a clean lubrication method that does not use oil. And ceramic SiO3N4 shows a super low friction in aqueous environment, like in this paper. So horizontal axis is a sliding distance, and vertical axis is a friction coefficient. In aqueous environment, SiO3N4 shows a very super low friction coefficient. And ethylene glycol is a molecule. Ethylene glycol is one of the molecules to improve the load carrying capacity in water lubrication. But there is a problem. The problem is the mechanism of improving the load carrying capacity in atomic scale is elusive. So we performed friction simulation of Si3N4, ethylene glycol, Si3N4 system using Allegro potential. So this is a simulation model. To compare with ethylene glycol system, we tried also aqueous system, Si3N4, H2O, Si3N4 model. We created the Si3N4 amorphous substrate and H2O area, and by pushing upper substrate and moving forcefully. The calculation condition is followed here. Okay, this is the animation of the friction simulation of Si3N4, H2O, Si3N4 model. So many times of friction occurs, and then after many times friction, ammonia and SiO2 particles are created. So ammonia and colloidal silica were also detected in experiments. On the other hand, in the case of friction simulation of Si3N4, ethylene glycol, Si3N4 model, the created molecules are so many types. For example, Si3 SiO2 particle, silicon alkoxide, hydrocarbons, and ammonia. Hydrocarbon, ammonia, and silicon alkoxide were also detected in experiments. So this is a larger view of the Si3N4 surface by ethylene glycol is absorbed on the Si3N4 surface. So after friction simulation, lots of chain and ring structure consisting of carbon and nitride are created like this: 5-membrane ring, 6-membrane ring, and a long chain like this. So we are considering that 2-dimensional graphene nitride is considered to super high contact pressure, support high contact pressure like this. Okay, second topic is neural network molecular dynamics simulation on element-dependent chemical reaction and oxygenated products during corrosion process of chrome, manganese, iron, cobalt, nickel, high entropy alloys. High entropy alloys is composed of 5 or more metal elements and shows a high mechanical strength but easy to occur stress corrosion cracking as I explained in introduction. Chrome, manganese, iron, copper, nickel alloy, it is called Cantor alloy, is the first synthesized high entropy alloy in 2004 as a new alloy composed of a solid solution of 5 or more atoms in near equal fractions. But this alloy has also a problem. The mechanism of stress corrosion cracking in atomic scale is elusive. So we performed tensor simulation under corrosive environment of counter alloy using Allegro potential. This is the tensor simulation of chrome, manganese, iron, cobalt, nickel, and adding alumina. So we change the amount of alumina. The amount shows X. If, sorry, please let me start the animation. I performed the tensor simulation for bulk system. So when X equals 0 and 1, the system deforms to create a stacking fault. Stacking fault means FCC to HCP phase transition. So on the other hand, when X equals to 2, that means aluminum is consists 2 times than other elements. In this case, the system transited to not HCP but BCC phase. This path is called Bain path. So we calculated the energy curve for, we calculated the energy curve in Bain path for each fraction, X equal 0, 1, and 2. The horizontal axis means the lattice ratio. 1.4 means FCC, 1.0 means BCC, and vertical axis is energy. If the system transform to FCC to BCC, in the case of X equals 0, the system must climb this energy curve. On the other hand, in the case of X equal 2, the energy barrier is very low and the potential energy of BCC is lower than that of FCC. This is the reason of the deformation mechanism. Also, we trying to corrosion simulation of counter alloy. This is the simulation model, like this is a high entropy alloy substrate, including not stacking fault, grain boundary. This system includes grain boundary and pre-crack to show the crack growth under high density water environment. So after this simulation, also the mechanism of deformation is the same. That is the stacking fault is created, but some chromium and manganese atoms formed oxide cluster with network structure like this. Chrome creates a passive film and manganese reacts with water or acid and elutes. So this is consistent with my simulation result. And iron, cobalt, and nickel less reactive compared to chrome and manganese. Okay, finally, I'd like to introduce new MLP model and present trends. There are the derivative model of Allegro. First one is Allegro Legat. This includes sharpness-aware minimization, which makes MLP model robust. By the way, Legat means smooth in musical terms. Second one is the force field enhanced neural network interactions, PENIX. This model is Allegro plus van der Waals and Coulomb long-range interaction by predicting charge transfer between atoms and atom volume. Third one is unified differential learning of electronic enthalpy and dielectric properties with exact physical constraints. This is Allegro model which can predict also effective charge and polarizability. The final topic is recent MLP model and trends. Recently, the derivative model of ACE is attracting attention. They are message passing plus ACE and mulch ACE. This is the integration of ACE and equip. On the other hand, efforts to increase the transferability are gaining attention. For example, Matrantis is the MD simulator using MLP, which can handle 96 elements like this. This transferability is caused based on the preferred potential and This transferability is caused based on the preferred potential and TNet developed by Matrantis company. The group of Professor Aichiro Nakano developed the foundation model of Allegro, which can handle 89 elements with low calculation cost. Recently, Meta company developed UMA, a family of universal model of 4 atoms. This MLP model is effective for not only molecules, but also materials, catalysts, and alloys. As such, the development and advancement of MLP is progressing at a very rapid pace. Okay, this is all my presentation. Thank you for your attention.
Okay, thank you, Dr. Fukushima, for your presentations. I think it is very inspiring from your presentation. We can see a lot of recent development of the machine learning potentials and application in material sciences. And I believe many of us here, both students and lecturers, are now reflecting on how these approaches could connect our studies and research, especially in physics and material sciences. And of course, I'm sure some of them may already have questions in mind. So let's move to the question and answer or discussion session. So feel free if you have questions, you can click the raise hand button and you can ask the questions directly to Dr. Fukushima, or you can type in your questions into the chat box and I will read the questions. Okay, any questions from our audience today? Yeah, okay, we have the first participants from Mr. Frankie. He raised his hand, so please, Mr. Frankie, you can ask the questions.
Hello, thank you, sir, for the time given to me. My voice is clear, sir?
Yes, we can hear you.
Okay, thank you very much, and thank you for Mr. Soga Fukushima today. Good theory today, and I want to say konnichiwa.
Konnichiwa.
I have 2 questions, sir. And the first question is, I want to ask about the neural networks. We know the activation function play a crucial role in introducing nonlinearity, enabling models to learn complex patterns. A common issue is the finishing gradient problem, where derivatives of the activation function become too small, slowing or even halting learning model functions up, as ReLU and Swiss were developed to mitigate this. So my question is, if an activation function can mitigate the finishing gradient problem, does that automatically guarantee a better model? How can we evaluate the quality of an activation function not only from a mathematical perspective, but also from the perspective of the model's generation ability? And my second question is, I want to ask about, in the practice, how can we distinguish whether a model is truly overfitting or whether it is actually capturing the genuine complexity that exists in the data? It's my question, sir, and thank you very much.
Okay, thank you for your question. So let me confirm the first question. So how it is like how to select which activation function is best? Is that correct?
Hello, sir. My question is the first is I want to ask about the neural networks to activation function is to we can look at from the function, not only from the mathematical perspective, but we have to look but also from the perspective of the model's generation ability. So if we have the complex model, how can we can evaluating it so do not have the overfitting?
Okay, so it is very difficult question, but maybe it's a general problem in machine learning region. So, but in the case of MLP, the condition of the training, activation, the selection of activation function, the symmetry function, and times of training, something like that, is used by investigating sometimes empirically, this activation function is good for these materials, but this activation function is not good for the other materials. So we must check which activation function is best for each materials or the system and each objective. If we want to reproduce the phase transition, this activation function is good or not, something like that. So my answer is, does it make sense? So maybe you have two questions. So please let me ask second question again.
Mr. Frankie, what is your second question again?
Okay, sir. My second question is I want to ask about in practice, how can we distinguish whether a model is truly overfitting or whether it's actually capturing the genuine complexity that exists in the data?
Complexity. Okay. How to guarantee? Okay. It's also very difficult question in machine learning region. For example, okay, let me explain the, okay, this one. Sorry. Yeah. So let me explain in the case of my research as an example. So in this case, we created about 10,000 DFT calculation data and trained Allegro model. After that, we tried a tensor simulation or like this. After perform tensor simulation, we calculated the energy curve of this vein first. And sorry, I cannot show here, but I calculated for also DFT calculation, and we confirmed that this curve is matched to MLP and DFT. So maybe this is how to guarantee the accuracy of the MLP. So not only this vein path energy curve, but also like energy curve in a reaction, by using the Nash elastic band method, we must check whether the MLP matches the DFT energy curve. So maybe, I'm sorry, my answer does not general, but this is how to check the accuracy of the MLP. Is it okay to this answer?
Okay.
Okay, sir. Thank you very much. It's clearly for me.
Yeah, okay. Thank you, Dr. Fukushima and Mr. Frankie, for the discussions. We have another questions in the chat box. Someone chat me. It is from Rizky. Let me read his questions. In Raman spectroscopy of vegetable oils using substrates like silicon wafers and iron via PLD, the spectra look nearly identical. From a machine learning perspective, could classification still be achieved with methods such as CNNs or PCA-based pre-processing, or would the similarity fundamentally limit this, requiring other analytical methods? So that is the question from Mr. Rizky. Please, Dr. Fukushima, if
Okay, I am sorry. I was looking for the question comment, but I cannot find. So could you please repeat again?
Oh, okay. He private chatted to me, so it is
okay.
not in the chat. Okay. So in Raman spectroscopy of vegetable oils using substrates like silicon wafers and iron via PLD, the spectra look nearly identical. From a machine learning perspective, could classification still be achieved with methods such as CNNs or PCA-based pre-processing, or would the similarity fundamentally limit this, requiring other analytical methods? Yeah, maybe I will also copy the chat into the general chat
Okay. Thank you so
box.
much.
Yeah,
So my understanding is
yeah.
about the Raman spectroscopy of okay. Thank you so much.
Yeah.
Sorry, I don't have enough knowledge about the Raman spectroscopy, but yeah, I think yeah, basically MLP can reproduce the structure and MLP can reproduce static and dynamic properties like radial distribution function and moving reaction of the chemical reaction like yes, as an example like this. Basically, so if the reproduce atomic coordinate, atomic force, and stress tensor, then maybe MLP can reproduce all properties, I guess. So maybe the question meaning like could classification still be achieved with methods such as CNNs or PCA-based preprocessing, or would the similarity fundamentally limit this? requiring as an analytical method. I am sorry, I cannot answer strictly, but I think it is, we need some other analytical method to like similarity fundamental limits. Yeah, basically the similarity must be satisfied is just all I explained. But in the case of the getting Raman spectroscopy, maybe other symmetry needed. If you want to, if you are interested in this this thesis, this thesis. So yeah, I would recommend to search how to get a Raman spectroscopy without other analytical method with a similarity fundamental limit, like which one? Okay, yes. Sorry, my answer is very rough, so this is all I can answer for now. I am sorry.
Oh yeah, sorry. Actually, Mr. Rizky updated his question. The peak of each graph is the same, only the intensity is different. He added.
I don't think so.
Okay, yeah. Let me. Yeah, sorry. The default settings of the chat box is only host to co-host. So now I have changed the setting to everyone and anyone directly. So Mr. Rizky, if you please if you can speak, you may speak directly your questions to Dr. Fukushima, or you can chat directly into the everyone chat box. Yeah, Mr. Rizky actually chatted me. He added information. The peak of each graph is the same, only intensity is different. Yeah, he added the informations about the question.
Excuse me, son. What is the meaning of graph? Graph means I showed in graph or this? Sorry. So are you asking about this graph? Or, sorry, I can't understand. The peak of each graph is the same, only intensity is different.
I think he meant the results from Raman's spectroscopy.
Okay.
I think
The graph means Raman spectroscopy, right?
Yeah.
Okay.
Oh.
Sorry, I'm. Sorry, could you explain by talking here? Can you speak here?
Rizky?
Mr.
Can you explaining by talking to Dr. Fukushima directly? Yeah.
I'm sorry, Dr. Fukushima.
Are you speaking?
I ini Raman spektroskopi of vegetable oils is the peak is from silicon wafer or Fa. It is intensity is different, but for the shape is same.
Kayaknya bisa deh. Can I help to explain the
Okay, thank you so
question of
much.
Rizky? I think the question is about experimental result, Dr. Suku. So maybe Rizky, yeah, try to characterize the sample that the sample is silicon wafer and Fa, and he tried to characterize with Raman spectroscopy, and then he get the result that is the peak position is same, but the position of the intensity is different, but the position of peak is same. And the question is, could we use your method to classify that difference? I think that the question means.
Okay, thank you so much. So it depends on the height of peak is what? Sorry. What defines the height of peaks of Raman spectroscopy? So I am not sure about that. So, oh, Mr. Rizky, thank you so much for attaching the graph. Okay. Okay, this one, okay. The position is same, but the height of spectroscopy is different, right? So your question is it possible to classify it by using MLP? Is that correct? Okay, thank you so much. So maybe it depends on the size of system, maybe. Sorry, I'm not specialty to the spectroscopy. So maybe the bigger size is needed to get high accuracy intensity. So if you use the MLP, we can increase the system size while keeping accuracy of DFT. So maybe you can get a consistent result by using MLP and perform larger system size molecular dynamics simulation. I'm sorry, I'm not sure how to calculate the spectroscopy from molecular dynamics. Sorry, my answer is again rough. Is that okay as my as a answer?
Okay. Is it enough, Mr. Rizky? Okay. I think it's we need a further discussions maybe outside of this Zoom meeting. Maybe, yeah. Yeah, thank you, Dr. Fukushima, from Mr. Rizky, yeah?
Oh, okay.
Okay.
Mm.
Yeah. Okay. Any other questions from the audiences? Anyone? Yes. Oh, okay. Our yeah, Dr. Eric raised hand, so please, Mr. Dr. Eric.
Okay, thank you, Mr. Danny. Before I ask a question, I would like to say thank you to Dr. Sogo for a very insightful presentation. After see your presentation, we can know that we can use machine learning in material science. And then from the participant, I also see there is Shimamura Sensei and also Shimochu Sensei. Thank you for joining our seminar. Nice to meet you again, Sensei. And then I have a question for Dr. Suku. My question is, actually, this is my first time hear about Allegro potential. Could you explain again about what is Allegro potential? Is it same with conventional potential that we all know, such as GGA or LDA? And then can we use that potential for conventional code like maybe LAMS and then quantum espresso and etc. Maybe that is my question.
Okay, thank you for your question. So your question about Allegro and how to use Allegro software and how to use this MLP, right?
Yeah.
Okay.
Is it
So
same with conventional potential such as GGA or LDA or etc.?
yeah, GGA and LDA is method in DFT, right? So
Yeah.
Allegro can train, not only Allegro, all MLP can train, not depending on the how to calculate the electrostatic calculation, like GZA and PB, GZA and LDA. So for me, we usually using a BUST to create training data using GZA PB potential and create a simulation, create a training data. We use the open source Allegro software to train MLP. After that, we use trained MLP and convert to the LAMPs. Basically, almost MLP model can use LAMPs. So for me, I use the BUST, but not only BUST, Quantum Espresso and CP2K and so on. They are the FPMD simulator is okay to use as a creating training data. Does it make sense?
Oh yeah. So actually, Allegro is software to train the data that produced from conventional code, right?
Yes, right.
Oh, okay, I see. And then in your opinion, what is the advantage of using machine learning potential compared with classical potential?
Classical potential?
Yeah.
So what? For example?
For example, like GGA or LDA, maybe.
Oh, GGA and LDA is not classical potential. Classical potential
Or
means like
maybe yeah, like potential for classical molecular dynamic simulation. I mean,
okay.
yeah.
I think it's in the case of Renaissance is too simple, but I think the case of reactive force field or
Yeah,
embedded
reacts,
atom method,
FF or etc. Yeah.
Yeah. For example, okay. For example, in this case, actually we tried to reactive force field potential to handle these 7 elements, but it was very, very hard to reproduce high accuracy. So on the other hand, embedded atom method is effective to reproduce the mechanical property of alloy, not only not only previous alloy, but also this high entropy alloy. But it cannot handle the reaction with corrosive like a water. So the potential which can handle this simulation is only machine learning potential, I think. So this is the large merit of machine learning potential. But for now, we are using Allegro model, but of course, the other MLP can handle this simulation, I think.
Okay, I see. So in certain condition, we can only use the machine learning potential, right? Such as this case.
Yes.
We cannot use conventional potential to calculate this case, right? And we only can calculate this case by using machine learning potential.
Yeah.
Okay, I see.
Yeah. To be honest, we can try this tensor simulation by using classical empirical model. There are presented empirical model for counter alloy. So we can try this simulation by using more right potential. But I think the accuracy is not higher than this MLP model.
But how about the computational time? Is machine learning potential need more time consuming than conventional potential? Or no?
Yeah, of course. Basically, MLP has a larger computational cost than classical force field, but the accuracy and transferability is very, very high than classical force field. So this is the merit of MLP. So if the objective is a very large system like 1 billion, 10 billion atoms, if you want to handle, MLP is not good to use. But if the system is like in this case, yeah, 23,000 atoms. Yeah, we can use MLP easily. In this simulation, we use only one GPU to perform simulation. So if we use multiple GPUs, we can increase into more larger system.
Yeah, I see.
For example.
So it is more time consuming.
Yeah, like
and this. Is the Allegro software open source or we need to pay license to use that software?
No, Allegro is open source software.
Open source. Okay.
Yeah.
Okay, I think enough for my question, Mr. Jenny. Thank you, Dr. Suku.
Okay, thank you, Dr. Eric, for the questions and insightful discussion with Dr. Fukushima. Any other questions from the audience? We still have several minutes for the discussions. Anyone from the audience? Yeah, I don't see any questions. So maybe I will ask my own questions, but maybe it is rather a simple questions because I'm very new to this kind of research topics. So basically, here in the Department of Physics, I work in the instrumentation laboratory. So mainly, we use machine learning, deep learning, and artificial intelligence is to for computer visions and object detections like that. So my question is uh, in instrumentation, usually we use the data, the training data, the validation data for our model is from photos. Yeah, so many photos like 10,000 and many other photos of an apple maybe. Yeah. So in these topics, machine learning potential for materials results is it the same with the ordinary machine learning where we need to gather a lot of data to increase our predictions, or is it different from the ordinary machine learning process? Thank you.
Okay. Thank you so much for your question. I think the basic problem is almost same, not only machine learning potential, but also image recognition, I think. So, but some part is different. Like in my understanding, like activation function, yeah, this one. In my understanding, it depends on the the best activation function is different in each projective. So in the case of machine learning potential, for now, switch is one of the best activation function, but I don't think this activation function is best for also image recognition. So each each researcher must check if activation function is best in this objective. So yeah, in summary, the basic problem should be the same, not only machine learning potential, but also image recognition. But very small part is different.
Yeah, okay. Yeah, thank you. Yeah, I think that's answer my questions. Yeah. Interesting. So basically they are the same, but in the activation function, maybe we have the different function. Yeah. Is that right? Yeah.
Yes,
Okay.
correct.
Thank you. Yeah. Okay. Thank you. Um, Another questions, maybe? Anyone? Okay. Okay. If there is no other questions, maybe we will close the discussion session. Oh, I'm sorry. We will still have a questions from,
Okay.
yeah. No, I'm sorry. Actually, it is chat questions, but he chat to my personal chat box. So I will copy and paste it to the everyone chat box because there is a molecular structure in there, I think.
Okay.
Yeah. So I cannot read it properly, so I will yeah, I pasted it on the chat box.
Oh, okay. The question is about yeah, this one. The question is about the SI3N4 ethylene glycol SI3N4 system. How does the distribution of ethylene glycol molecules between the two SI3N4 surfaces affect the frictional behavior, particularly in terms of reducing or enhancing the frictional force? So basically, the conclusion of this research is the carbon nitride makes high contact pressure, not decrease the friction force. So this is important because in experiments, ethylene glycol is used to improve the load carrying capacity, not decreasing the friction force. So I cannot show here, but we calculated the friction force during the friction simulation, but the friction force is higher than H2O system. So, yeah. In summary, the ethylene glycol makes only higher contact pressure, but it doesn't work like a decreasing of friction force. This is our conclusion of this research. Yeah, so maybe ethylene glycol enhances the friction force.
Okay, thank you, Dr. Fukushima, for I think it's Miss Inani. I hope the answer is enough. So, ladies and gentlemen, thank you for the engaging questions and insightful discussions. Yeah. Unfortunately, due to our limited time, we have to bring the Q&A sessions to an end. Thanks a lot for all participants and especially to Dr. Fukushima for the discussions. And before we officially close the lecture, maybe I will ask one last question to Dr. Fukushima on behalf of our students. So, since many of our participants today are physics students, especially undergraduate students who are just beginning to explore research opportunities, do you have any final words of encouragement or motivations or advice to motivate them to pursue research in the field of material science or machine learning in material science, particularly how their background in physics can contribute to advancing this area? Please, Dr. Fukushima.
Okay, thank you so much. It's important question. So my recommendation is for now, let's use any open source software to train MLP, like not limited Allegro. There are lots of open source MLP software, and not only MLP software, but also already trained MLP is presented in a lot of papers. So if you want to, if you are interested in molecular dynamics simulation, so I recommend to use any machine learning potential presented in other papers. And maybe I think you can understand the merit of machine learning potential. So after that, if you have any topics you want to investigate, so such as I want to calculate thermal conductivity, electronic conductivity, and mechanical property, and reaction, chemical reaction, and so on. So you can, if you can use the reported potential, it's okay to use that potential. But if you don't have any effective potential, you can use open source software to train MLP. Of course, you must perform some past principles MD simulation to get the training data. So anyway, I recommend to use machine learning potential to understand the merit.
Yeah, okay. Thank you, Dr. Fukushima, for such inspiring closing words. Yeah. Thanks a lot once again for the presentation and discussion from Dr. Fukushima. And before we officially conclude today's sessions, it is my honor to present a token of appreciation to our distinguished speaker, Dr. Sogo Fukushima. So, on behalf of the organizing committee, we would like to express our deepest gratitude for the insightful knowledge and inspiration you have shared with us today. Your contribution has greatly enriched our understanding and motivate us to further explore this field. As a symbol of appreciation, we would like to present this certificate of appreciation to you, Dr. Fukushima. This is the certificate of appreciation. Thanks a lot once again for the insightful presentation and the discussions, answering the questions from our students and our general audience. Thanks a lot, Dr. Fukushi.
Yeah, thank you so much. And I am sorry for my poor English to answer your questions. So thank you so much for giving me a valuable opportunity to lecture in English.
Okay. Thank you. So, ladies and gentlemen, we have now come to the end of our today's general lecture. On behalf of the committee, I would like to once again express our deepest gratitude to Dr. Shogo Fukushima for sharing his expertise with us today. I would also like to thank all participants for your active engagement and thoughtful questions. We hope today's session has been meaningful and inspiring, and may it spark new ideas for future research and collaborations. With that, I officially close this event. Thank you very much and see you at our next academic gathering. Have a wonderful day. Wassalamualaikum warahmatullahi wabarakatuh.
Waalaikumsalam.
Thank you.
Waalaikumsalam warahmatullahi wabarakatuh. Thank you.
Terima kasih Bapak Ibu yang sudah hadir. Thank you Sogu for your time. It's very nice presentation. Yeah.
Thanks a lot.
Hopefully we can organize